Okay, so now that we have the tools to evaluate whether an equilibrium is subgame perfect or not, let's apply those tools. And let's apply those tools in particular to the Grim trigger strategy. Remember, in the Grim trigger strategy, SI is C if the history looks like, up to that point, looks like C, C, C. Okay. Basically, your opponent up to that point, I'm going to call this BJ R equals C for all R, where R is for period 1, 2, 3, 4, up to that point, all of the periods that have transpired, and D otherwise, if this strategy is a subgame perfect equilibrium. We know that it is a Nash equilibrium, but let's check if it's subgame perfect. It's a Nash equilibrium because if your opponent is following this strategy, then you have no incentive to deviate. Okay. How do we check? We're trying to disprove that it's a subgame perfect equilibrium, so it is sufficient to show that there exists one history, one subgame even, at which the one deviation property is not satisfied. So suppose after CD has occurred, suppose we're in the subgame after that. So CD has just occurred. Up till this point, it's just been cooperation, or there has been no history. And let's say CD has occurred. Then for player 2, the strategy should just be C. Because for player 2, player 1 has never deviated. For player 1, the strategy will be D. And so in the next period, you end up with DC giving player 1 3, player 2 0, and then after that is just D. Right, and it's DD forever after that. Does either player have an incentive to deviate from this? I argue yes, and the reason is that player 2 here, knowing that player 1 will be playing D, and that the equilibrium will be DD after that, all outcomes will just be DD after that, should profitably play D here and not C. It just wouldn't make sense for player 2 to play C. Right, so in a strictly dominant sense, here in the subgame, player 2 has an incentive to deviate. So this is definitely not a subgame perfect equilibrium. It is, however, a Nash equilibrium. It's a Nash equilibrium because remember, the Grim trigger strategies, both players, if the history is null, then they play C. So the only outcome of the Grim trigger strategy is an outcome of CC forever. And yeah, so this subgame never actually arises, and so we don't run into any issues, and so it's still a Nash equilibrium. Okay, now one more, actually, there is another deviation here that's possible, and that is if delta is greater than half. And again, remember that the game that we're considering has the payoffs that we had defined earlier, 2, 2, 0, 3, 3, 0, and 1, 1 from C, D, C, D. This is the payoff matrix of this game that's being played in every period. If delta is greater than a half, then player 1, even though player 2 has cheated on player 1 here, player 1 has an incentive to just keep playing C rather than switching to D, with the hopes that player 2 will continue to play C. You see, what happens is if CD has happened, then that means that player 2 has cheated on player 1, right? So think Russia has overproduced oil and Saudi Arabia is pissed off about that. Makes sense. But however, if Saudi Arabia is sufficiently patient, then they would continue cooperation with the hope that the Russians would come back to cooperate again with them. Because the payoff from cooperation is just so much higher than the payoff from when both parties defect. Also, we can modify the Grim Trigger strategy so that we do not run into this problem of the game being so that we can have a Grim Trigger strategy which is also subgame perfect. So let's do that next. So we showed you that this Grim Trigger strategy is not subgame perfect because for any discount factor, player 2 has an incentive to deviate, and for discount factors that are greater than equal to well, if the discount factor is strictly greater than a half, then player 1 has an incentive to deviate. Okay, so let's modify the Grim Trigger strategy. The way we modify it is by having two states. So there is a state in which we cooperate and a state in which we defect. Right, that holds true for both players. And the only way we go from the state of cooperation to the state of defection is if we have any outcome other than CC. So if we ever have any outcome other than CC, then both players will always defect. If we have any outcome, if we have no outcome so far, or the outcomes so far have all been CC, then both players continue to cooperate. And we can show that this is subgame perfect simply by using the one deviation policy, one deviation property. Okay, there are two possible subgames. One in which all future outcomes are CC, and the other one in which all future outcomes are DD. If all future outcomes are CC, then player 1, okay, this is subgame perfect, I should mention, for all delta greater than or equal to 1/2. So the players have to be sufficiently patient, because otherwise they can't sustain cooperation at all. Okay, CC. So if all future outcomes look like CC, then the average discounted payoff is 1 minus delta times 2 plus 2 delta plus 2 delta squared plus so on and so forth. Because you get $2 in every period, but you discount, you multiply discount factor delta for every period of delay. And that simply is equal to 2. Because this is equal to 2 divided by 1 minus delta. If you ever deviate from this, so you play D instead of C, you get 3 for the period in which you deviate, and then you get 1 in the period after that, multiplied by delta, because that's a discount factor for delay, plus delta squared, plus delta cubed, plus so on, because you are earning $1 in every period, because that is the payoff that you get when both players play D. This equals 3 minus 2 delta, the average discounted payoff. So If 2 is greater than or equal to 3 minus 2 delta, then you don't want to deviate even for one period. And this is equivalent to saying that delta is greater than 1/2. Right, because then you have 2 delta here, this becomes 3 minus 2, divide by 2 on both sides, and so that's simply delta greater than 1/2. Now let's see, and this is simpler. If you're in a subgame where all future outcomes look like dd, because that's that state, then your only choice right now is whether to play D right now and get 1 in this period, or play C right now and get 0 in this period. Nothing you do in this period is going to change the future path at all, so, you know, you'd rather get 1 right now than 0, basically. So what that means is if Russia and Saudi Arabia, they're both defecting, so they're both producing a lot of oil, it doesn't help Russia or Saudi Arabia to cooperate for one period. It just doesn't make sense. The other player's going to continue being non-cooperative, and you know you're going to continue being non-cooperative in the future, so why cooperate right now? Also, to be clear, to clarify one more thing, when we talk about one period deviation, we don't mean that your action is changed only for one period. It means you don't follow the strategy for one period. And then the period after that, you go back to following the strategy. Here, this is the strategy. The strategy is to play C if you've only observed cooperation so far, or you've observed nothing so far, and D afterwards. And so here, when we consider a one period deviation to cooperating forever, what we mean is that we deviate in this period, so we choose D even though we've only observed cooperation so far, and then we go back to playing the strategy, which in this case would prescribe continuing playing D, because in the previous period, now, because we deviated, we observed an outcome that was other than CC. Okay. So I hope that makes sense. A one period deviation is a one period deviation from your strategy, not a one period change in your action. At least not necessarily. Like in this case, that's definitely not what's happening. Your action changes forever because for one period you deviated away from your strategy. Okay. Also, before I end this, I wanted to go back to the previous video just to add one more thing. Remember the set of feasible payoffs that we had when the payoff matrix looks like this? 2, 2, 3, 0, 0. Always do that. 0, 3, and 3, 0, and 1, 1. Looks something like this, and this shaded area between this diamond is the set of feasible payoffs. If, on the other hand, we had a payoff matrix that looked like 2, 2, 1, 1, 0, 6, 6, 0. Again, this is a prisoner's dilemma game. The only equilibrium is this one where you both deviate. But the payoff matrix, the set of feasible payoffs, rather, will look like this. This is 6. This is 6. This is 1 and 1. So the set of all feasible payoffs will look like this, where this point is 3. right? And in fact, a really profitable strategy here in this kind of situation is where we take turns cheating on each other. So in one period, you overproduce the oil, and in the other period, I overproduce the oil. And so on average, both of us get an average discounted payoff of 3 if we're sufficiently patient. All I really wanted to show you here is that the set of feasible payoffs don't always need to look like a diamond. They can look like this kind of weird triangle as well. And basically, the set of feasible payoffs depends on what the payoff matrix looks like. Okay, see you in the next video.